So it took Joe Rosell about 9 months to complete the segmentation. The thing we learned about ITK Snap, as powerful as its automatic or semi-automatic segmentation capabilities are, is not good enough to segment, that is, to delineate individual anatomic structures when the intensity of the pixels at the boundaries are not different enough. And so if there's isodense intensities, and you know the structure is in there, you have to go in and manually segment it. We needed to segment 79 structures for this model system to be useful in our curriculum. So they, all but I think 2 of them had to be manually segmented. So now picture, if you will, that means Joe Rosell, medical student between first and second year, had to hand color, that is, click a color label for every pixel for every structure that we wanted to delineate. Now we knew why no one had done it before, right? Who with the knowledge of neuroanatomy would have this much time? Only Joe Rosell. And only that year, I have to say. There's no way he could have done more after second year or beyond. And so when he couldn't identify a structure simply based on the intensity of the pixels on the MRI, we used experts, neuroanatomists who had done serial sections of human brain. We used atlases as resources. And so he made truly educated approximations. And it's pretty good. I'll show you in just a minute. So, but this wasn't the end, because as you can, I hope you can see from this picture, this is the main screen on ITK Snap. And all of these options on the left are editing tools. Well, when we first ran this for our medical students, they started editing all the database, and they were making a mess, and it was really frustrating. So we realized very quickly that if this was really going to be a useful tool, we had to create a simplified user interface that prevented them from editing any of the database. And so to do that, we actually got an undergrad from RPI, Aaron Ash, and we paid him a summer undergraduate research fellowship, and he worked full-time all summer, and he compiled the source code for us, which was actually quite a bit of work, because there are lots of tools inside, embedded in ITK Snap, that had to be compiled first. But he used a concurrent version system client to compile it, and then Visual C++, and that allowed him to then change the appearance using this fast light toolkit application called Fluid, which allowed him to move the menu buttons and to redefine some of the features on this user interface. And so once all this was done, we reposted the altered code as required by this Berkeley-style open source software back to the original ITK Snap site, and made this available to not only our students, but anybody that wanted to use it by simple license and download from the Albany Med website. And this is what it looks like now. And rather than list all these things for you, I'm just going to show you how it works. So basically, just to orient you, one of the things that is on this slide that I want to remember to tell you is that the size of the files that open and install on your computer total for all that data, it's 150 megabytes. It takes up so little space, our students have no problem downloading it. It runs very quickly, especially if you have a quick processor. At the moment, it's only compatible with a PC, but we have people using it on a Mac because they have a program that slaves their Mac to act like a PC. Right? So it's very easy to use. You can export the files, or the models that you build, to PowerPoint or Adobe. You can print them, you can save them. So let me just show you. Like I said, I think it's a waste to keep going through. Here are some examples, though. Very pretty pictures can be built using this. These are all custom models built using this software, and you can do things for teaching purposes, and a lot of our educators actually have used these to do it, to create a model that allows them to make a specific point, and they could go through textbooks for a week and not find just the right one. So this has been very helpful for faculty as well as for students. Before I open the program and show you how it works, once again, Joe Rosell did the lion's share of the work since he manually segmented all these 79 structures. He's now an MD, about to start a residency in radiology, perfect match. Aaron Ash is an engineer, as I said, from RPI. And then, you know, the other faculty people that have been working with the students really have been neuroanatomy experts, or myself, I'm the grant writer and the curriculum integrator. So this is the website that you can download the program from. And I will just shut this down for now and go to my software. So when you go to the website, it asks you to agree not to make money off of this. And once you've agreed to that, you can download the program. It puts a small icon on your desktop that's called the installer. When you double click on that, it installs 2 icons on your desktop. Actually, they look just like... No, I don't want to do that. It didn't like that. All right, so what we're looking at while it's thinking, what we're looking at is the standard user interface page for the software. And you can see there are the 3 standard imaging planes for MRIs. And we like the fact that our students can correlate what they see in the 3D window with what they see in these images. Oh, please don't not respond. Hang on. I'll just open this up again. So, it never fails, right? It's Murphy's Law. I've been playing with this thing all day. While this is deciding what to do. So on the left, we have buttons that allow you to change the overall MRI color opacity, which means that you can look at an MRI in grayscale totally, or you can see all the colored structures visually. This slider up and down will allow you to scroll through the axial images from the chin, or from the neck all the way to the top of the head. This is a sagittal slice view, so it scrolls back and forth when you use the slider. And this allows you to scroll from front to back. This is the window that has the 3D models, which unbelievably will not work.
Is software used diagnostically?
No, and it's not. There are other 3D rendering software that's used clinically. They don't have this kind of ability to delineate structures that can't be viewed on an MRI. That's really the power of this, is that we needed to be able to see things that you really just could not see otherwise. So let me just open up. I don't know if it'll let me open up another of these. I'm so sorry. This is awful. All right. Let me see if I can open a version of this that won't take up too much RAM. All right. Good. I think I'm mostly closed now. So let me try again. So this is what the icon looks like on your desktop. You double click and it loads the database. It'll run faster on newer computers. Mine has a slower processor. But it takes between 30 seconds and 2 minutes to load the model. So we're watching it load. Agonizing. Okay. So let's jump right to the 3D window. So you can view any of these windows. Remember I said you could scroll up and down through these models. And you can change them so they look like an MRI, or so you can see the color. But this is the window that most people spend their time in first year. And so we can zoom. And right now I'm looking at everything that has been colorized. So I've essentially got show all viewed here. But if I wanted to look at some pre-built models that are particularly useful for students in our program, we could look at just the ventricles. We can rotate the ventricles in 360 degrees. We can change their color. I don't like red ventricles, looks too bloody, so I'm going to make them, I'm going to make them blue. I think I like ventricles to be blue. So as long as I have the ventricles listed on the selected structure, I can change the features of the ventricle. I can change their opacity, make them see-through. So I can also use any of these pre-built models, basal ganglia, cerebellum. There's several of them that our students find helpful. But I went ahead earlier today and made my own model. I can browse and find that model again pretty quickly and load it. So I like this model because, first of all, I like the colors. I'm sorry if anybody's colorblind. So this model shows me those ventricles again, but now it shows me the relationship of the hippocampus. And the hippocampus is this green structure. The green structure is located in the inferior wall of the medial wall of the inferior horn of the lateral ventricles. And so here's this lateral ventricle, here's the hippocampus, and it has this yellow fornix reaching up. If you're not sure that that's the hippocampus, the way students will use this, they'll click on this structure browser and say, oh yeah, that's the ventricles, and I want to click on the hippocampus, make sure I'm looking at the right structure. Yeah, that's the hippocampus. It's also listed in the selected structure description. And so there are 79 different ones of these. If you say, well, I want to know how the basal ganglia are related to the hippocampus, you can click on the basal ganglia, and now we can see that. And remember that weird alliance of abnormal bone growth and infertility and double vision I mentioned? Well, that would be a tumor that would affect the pituitary, the hypothalamus and pituitary. So I'm going to show you why that particular location for a tumor would cause that kind of a problem. So the pituitary produces hormones, one of which is growth hormone. If you have an excess of growth hormone because your tumor is producing too much of it, you tend to get this overgrowth of bone, particularly in the face and some of the small bones in the hand. But you also will get double vision because, as you can see, the optic chiasm, here's the optic nerves coming from the eyes here and here, the optic chiasm sits right above the pituitary, which is right here. So now we can teach a student how these kinds of relationships result in clinical deficits. Again, sorry for the little technical glitch. It really does work pretty well on most computers. So I'll take questions.
Question?
Mostly a comment. So just want to congratulate you for sending back your modifications of the code to regional developers. There are many communities in open source that are happy to use the code, but not always happy to send the improvements. So.
Yeah, we're happy to do it.
Did you guys know that you'd both be here?
No,
until the program went out.
I wish I have seen your talk yesterday because last night I was segmenting ventricles by hand.
Yeah, it's a real job, but honestly, that is the reason that this kind of software had not been produced before. Now, I should say, if there's anybody in this room that really loves anatomy and also has the kind of facility to work with this kind of software, we are developing additional anatomic model systems. We're working on a female pelvis right now. We're trying to focus on anatomy that's difficult for students to learn because the spatial relationships are really hard to see. So we're always recruiting people who have some of the tech savvy. Jones room.
I think we have some of that in this room.
I was kind of hoping. That's why I came out here. Yeah. Anyway. Yeah.
Any other questions?
Thanks.
All right. Thank you, Tara.